Hey, welcome to the Monday 5:30 section of 2440, and we're in section 2.3 of the book. So if you've ever wondered what the difference is when people say I got a 16-bit computer or 32-bit, or when you download Windows and it says, you know, do you want the 32 or the 3264 version, what that stuff's talking about, it's talking about the size of the container that everything is built around inside the computer. And it's called a word. So a word can be any number of bytes. We always say it's the size of however many bits that is, though. So if it's a 16-bit architecture, we could also say it's a 2-byte architecture. Or if it's 32, we could say it's a 4-byte. But we always say bits for some odd reason. And everything is built around that. So the system that we're using in the book this semester is a 32-bit architecture from a manufacturer called MIPS. And that's whose assembly language instructions we see in the book. It's similar to ARM. In fact, they're all similar to each other up to a certain point. They all have the same basics. But what's different about a lot of these is the number of bits that you carry around for everything. So in the case of MIPS, since in this example it's a 32-bit architecture, there is a 64-bit version flying around out there too. It means all of our registers are 32 bits in size. All of our addresses are 32 bits long. All of our integers are 32 bits. If we want to represent a floating point number, we need to do so in a 32-bit number. If we want to pass data into the CPU, it's going to be across 32 wires. If we want to pull something off of a hard drive or into a network card or push it to layer 2 cache, it's always going to be done in quantities of 32 bits at a time. So if you look at the address bus that you drop 32 ones and zeros on to tell some device which address you're dealing with, it's 32 bits. Right? Here's the problem. RAM doesn't care about words. RAM is built around bytes. And we want RAM to work on a whole variety of different computers so that it's cheap. We want it to be as close to free as we can get. I mean, it's bad enough, it's expensive enough as it is, right? So if we build a system around 16 bits, 32 bits, 64, we still want to be able to use the same RAM provided that it's the right speed. So for this reason, we decided RAM is not going to deal with words. RAM will just deal with bytes. So we're going to need something to stand between our kingdom of words and this byte-oriented RAM that we've got and translate between the two, such that if I ask for a certain word in my computer, so to load it from RAM, for example, what I need to do in RAM is get to the right starting address, pull that byte, and then the next 3 bytes as well, which is exactly what we'll build circuits to do inside these types of systems. So there's a mismatch between which address are you really talking about. Because if I'm telling you, you know, the fifth thing, not the first or second or fourth, but the fifth one, and I'm doing it in a register, do I mean the 5th byte, or do I mean the 5th word, which would be the 20th byte, and the 21st, 22nd, 23rd? So we've got to nail down the nomenclature we're going to use, and this turns out to be far more important than the tedious nature that it might sound like. Let me give you some examples. Suppose you have an Excel spreadsheet, and you store something like a number, and you are running on a 32-bit computer. So you save the file, and you put it in Dropbox, and somebody else in the class opens it, and they're on a 64-bit Windows machine. They open up the file in Excel. How is Excel supposed to interpret what's in that cell? Is it a 64-bit number now? Because they're only going to find 32 bits. Is it going to be the least significant or the most significant 32 bits? Are they going to misinterpret it as half of a 64-bit number and lump the next one on with it as well? So this is stuff we never, ever think about when we're doing something as simple as dragging files around, emailing them, putting them in Google Drive, etc. But systems are different, and so we have to worry about this intermediate format. So this has led to a lot of work in the standards bodies to try and nail down the file format and exactly the number sequence we're going to use, given that different people have different architectures of computers. And it's even worse than that. There's something called endianness, which we'll hopefully get to by the end of the lecture. So that's an issue. And if you are asked, which version do you want to download, that's going to kind of box you into creating files in that format. So understanding how things get between storage and our system is important for more reasons than just how many address wires you've got. So we call it a word. And with words, you're going to build registers the same size. So I'm going to switch over to my sketchpad, and I'm going to draw some things and ask you guys some questions. So let's say this is my CPU. And I'm going to surround my CPU with registers, because the registers are as fast as the CPU, and they are the last place I put things before the CPU works on them. So for example, when we get to the chapter on arithmetic logic, you'll see this little shape. And this is the arithmetic logic unit. And this is the brains of the outfit. Why it's drawn like this, I don't know. It looks like a giant greater than sign sort of to me that had a bad day here over on the right. But what happens is you feed, let's say it's a 32-bit computer, you're going to feed 32 inputs here. And if it's an instruction that needs 2 inputs, like addition needs 2 inputs, then you're going to feed 32 more here. And you're going to do the magic, because you're going to have control circuitry that comes in here and tells it what to do with those 1 or 2 things. You'll also find most systems have a little flag that gets set if the result is 0, because it's really important. People want to know that. And the result is going to be maybe 32 bits, maybe more. So we usually won't draw 32 little wires. We'll just draw 1 wire and put a line through it and put the number of wires over it. So where does this come from? It's going to come from a register. And you've got to have the registers close to this so that you can pick the one that you need and feed its 32 bits into the ALU. So for that reason, I'm probably going to build my CPU with these things physically surrounding the CPU as close as I can get. And so here's the deal. Somebody's got to keep track of what's in each of these 32 registers, and they've got to decide when I don't need what's in one of them anymore, and it's available to hold something else for an upcoming instruction. And I'm constantly trying to guess. I got 5 instructions coming up. They need a total of 15 different registers. I pray they overlap somewhat, but let's say it's the worst case. I'm going to add 2 numbers into one location and then add 2 other numbers into a separate location and continue that for 5 times. That's 15 different registers. I need which 15? And who's going to pick them? Your compiler will try to pick them when you write your code if it knows exactly what's going on. But it doesn't always know. But let's say it's add into T0 what's in S0 and S1. So that's pretty, you may have called that add C equals A plus B. That may be closer to the C code that you wrote. The compiler is going to convert that into register numbers. So if 32 is decent and it's kind of a race to get them in there, why not have 1,000? I mean, why not have 1,000 registers? How? How is it slow? Why would it take more time, though? You're right. That's the answer. Why would it take more time if I had 1,000 registers? But the instruction will tell you which register to go. Let me give you a different analogy to think of. Let's say you have a pizza delivery service, and you're going to release all of your drivers at once. They all go and deliver their pizza, and they all come back, and you're trying to calculate how many drivers do I need to hire. And you decide that the way you're going to calculate this, because synchronization is very, very important to you, you can't have them coming and going at different times. You want everything to be ordered and regular, so you're going to figure out the furthest address away that you can go to and figure out how long it takes you to deliver a pizza there and get back, and however many of those you can do in an hour, that's divided into how many pizzas you want to sell, that's how many drivers you need. So if that's your analogy, then why not 1,000 registers? What are the registers in this case? They're the addresses. So if you have 1,000 registers, some of them are going to be over here, right? That takes longer. She's right. It's the time it takes to get there. Remember, the speed of electrons in metal is a limiting factor in chip speed, believe it or not. It matters. We want to go as short a distance as possible. So if you've got one person out here in the suburbs in spring that because he's your brother-in-law, you're supposed to deliver him pizzas too, he's going to screw up your clock because you're going to have to wait on that register. If it's used, potentially, you're going to have to wait that long just to be sure. So you can't ever have a clock on a CPU that's any faster than your slowest register. If you can't build registers as fast as your clock, you cannot have that clock speed. It is a limiting factor in chip design. So registers are made out of the very same silicon, at the very same time, with the very same chemical process, right next to the chip with the same electronics. It's built in as part of the chip. It's on the surface of the chip. And you may build them in 3D to surround the ALU, because that's the last chance you have to get something before the ALU is going to grab it and calculate with it. All right, so for whatever reason, you know, speed is one of them, but it's not always the dominant factor. And maybe some of the older systems, everyone kind of huddles around 32. There's some systems with 64 and some with 16, and we've experimented with some others. But for the vast majority, 32 is the number. Why? Because the most complicated math operand you can think of has 3 operands, 2 inputs and an output. And you're willing to write code that way if you're a compiler operator. So if your memory is 1/5 the speed of your CPU, then you need to be 5 instructions ahead kind of at any given time. You know, it works out. The math suggests that you don't need a million of these things. A handful will work. That's not completely intuitive. It's a little surprising. Even as chips get faster, we still stick with that same number of registers. In mobile phones and in other devices, it's either a half or double or 32. It's right around in there. Yeah. Oh, sure. Everything increases the amount of power. But what you want to do is lower the cost a little bit and not have to use as dense technology because it's easier to manufacture. You have a higher success factor, meaning fewer defects, because it's more established technology. You're better at doing it. You're not dealing at such a level where, you know, atoms of width of wires become a big problem. In manufacturing chips, gamma rays passing through the building can destroy your chips, and they're passing through us all the time. They're just so small that they don't hurt us. Our bodies can replace anything that's damaged, and we never know. It doesn't affect your vision, hearing, you never know it's there, but it's happening constantly. But on chips, it'll ruin them. So some chips have to be shielded if they're going to be used in nuclear environments, for example, if they're things that can be generated and pass through. But if you deal with less expensive memory, where everything's bigger and wider and easier to make, then you can have a lot more of it for the same price. So we try to abandon as fast as we can the riskiest part of the system and use more stable, secure, cheaper if we can. Okay? So clock frequency has to go down if you move things further away. She nailed it right up front. You're the first person to do that, by the way. Just like that, you have the answer. Okay, so if we want to add things, we use in C and most other programming languages variable names. And as we saw last time with commands, we have operands, but we have these register names. You guys remember the register names we looked at last time? Like $T0 and $A1 and things like that. So it's the compiler's job to convert our variables into the register numbers that it wants those values to be stored in right before the ALU is ready for them. So the compiler can reuse the registers all throughout the program, and it's going to have to because there's only 32, and you might have a million lines of code, but it's keeping track of which ones it's using in your vicinity. So that it's putting things in registers, it's asking the system to put things in registers a few lines ahead of when you need them so they'll be there in time. That's kind of the idea. So if you have a problem like F equals G plus H minus I plus J, and you store those, as they say here, in S registers S0 through S4, then the way that's going to get calculated is you're going to write an instruction that's going to add G and H first, and you'll store that in a temporary register. And then I and J next, and you'll store that in a temporary register. And then you can subtract one from the other. And now you have your answer. So how do you know whether it's going to be T0 minus T1 or T1 minus T0? Where would you look if you needed to be sure? The appendix. That'll get you part of the way there. But the appendix will tell you what the operands are and where they are in the instruction word. But believe it or not, the appendix doesn't tell you the formula. For that, I know. For that, you need the reference card that's in front of the book. That's also a PDF along with the appendix that's in the Google Drive. So I'm not going to share it on WebEx because I'm only going to take a peek at it for just 1 second. But if you look in Google Drive in General Info, under Extras, under Extras, there is a MIPS reference data card. And if you go down to subtract, it says RD equals RS minus RT. That with the appendix tells you it's T0 minus T1. Thank goodness, because that's what you guess. So in this case, it is what you would guess. So anybody written an assembler before? No, you just did. You can all raise your hand now because you just did, right? So you just wrote assembler. It is the compiler's job to pick what registers to use, not you. You can sometimes include assembly language commands in C. Most systems give you the ability to bail out and pass something that you want the compiler not to compile that's already assembler. And you can say, hand the CPU this instruction. Well, that's kind of a vector for attack sometimes. You have to be a little bit careful, but there's usually a way to do that. So if you take your compiled program and you move it to a different system, can you run it again? Can I take my assembler and run it on a different computer? If and only if what? It's the same exact architecture. Exactly the same. If not, then you take your higher level program written in C, and what do? You move it to the new system, and then what do you do to your C program to get it to a point where it can run on the computer? You recompile it. The compiler has to know the details of your architecture, and so the compiler usually comes from the operating system vendor. And it's built specifically for that OS running on that specific computer. So again, it's a little tricky if you take a compiled program and you put it up in Dropbox and you want somebody else to run it and it's an assembler. Maybe some of the commands will work, but it's dangerous. The same thing with an executable file. If you then take the assembler and convert it into machine language, usually systems will spot a mile away that it's not for them. This stuff won't even work right. So this is why we want abstraction. You don't want to have to learn assembly for 15 different computers to run the same C program. You would like your app to run on all Android phones, not have to write 50 different versions for 50 different Android phones that use 50 different versions of ARM chips. You want to write once and then let somebody else recompile in that environment. That's kind of the scaling bit. Okay, let's shrink down a little bit and try a couple of exercises here. So suppose we have T3 is equal to T4 plus T5, and T3 has 0. Currently, T4 and 5 have 28 plus 16. So what's the right assembler line of code to run this and to convert this C language, sort of quasi-C, into assembler? Well, the instruction is going to be easy. They only give us one choice. It's an add. Should this be T3, 4, or 5 over here? 3. Okay, what about this one? 4, and this one? And let's check. Ta-da! So that's what we've got. So little baby step there. If you want to transfer, here's a section where I'm going to pick a bone with the book. Does anybody remember back in physics class in high school when you first learned the model of the atom? And then a day later they told you it was a lie, it wasn't really the model of the atom, and then they taught you the next model of the atom, and then a day later they told you that was also a lie. And I remember, like it was yesterday, 1979, Kenneth Terrell was my Chemistry 2 teacher at Putnam City North High School in Oklahoma City, and I was facing west. I have one of the weird things about me is I remember the direction I'm facing at all times. I'm facing about 274 degrees right now. Just don't ask me how I know this. Wherever I am on Earth, that's how my memory works. So he taught me the wrong model of the atom, and I was upset and said, like, why are you wasting my time? This is wrong. Why don't you just jump to the end and teach me the right one? So he moved about 4 degrees to the south. No, I'm kidding. And he tried, and I didn't get it at all. It just went completely over my head. And he goes, and that is why I'm the teacher and you're the student. So what this book does, I appreciate. They're trying to kind of do the same thing and get us built up to the way addressing works, but I think it's too little. I think we can totally get our heads around this. So I'm going to point out the way the book does it. I'm going to point out how it's wrong. And fortunately, they're very, very quick to move on to the correct way of doing it, but it's going to confuse the heck out of you later if you go through it and you're not sure which one was the right one. So I'm going to try to be super clear. So here's the deal. You remember how I told you RAM deals with bytes and we deal with words? And if I need to get like the 5th word out of RAM, because my words are 4 bytes each, what I really am interested in is the 20th through the 23rd byte. That's where the 5th word is located. It's not located in address 5. In address 5 is like the 2nd byte of the 2nd word or something like that. So I'm going to have to build some circuitry to go and grab however many bytes are in one of my words. So here's what they're showing us is if I want to transfer data to RAM, I've got 4 pieces of data here. The addresses are not 0, 1, 2, and 3. The words are word 0, 1, 2, 3, but in memory, this is address 0, 4, 8, 12, 16, 20, 24, and so on. If this was a 64-bit architecture, this would be address 0, 8, 16, 32, so on, counting in 8. If it's a 16-bit architecture, it would be 0, 2, 4, 6, 8, 10, 12, 14, so on. But we're in a 32-bit architecture. So 32-bit architecture means I have 32 bits in each word. That just happens to be 4 bytes. So anything I send to RAM, I'm going to send 32 bits at a time. RAM's going to see that as 4 bytes. Anything I get out of RAM, I'm going to get 32 bits at a time. RAM's also going to see that as 4 bytes. So it's going to give us that stuff at a time. So I'll need a piece of circuitry to do between the two, but this is not the correct addressing. If this is a word address, yeah, but in memory, it's never the address. It's always in multiples of however many bytes you have in a word. So if I come down here a little bit and we look at an example, if we want to add whatever the value is of this variable h to the 9th element of array 8, the first one being A0, therefore the 9th one being A8. And I want to write the assembly language code to interpret this. The way you're going to deal with arrays in assembler is not unlike the way you handle them in C. You need a base address where the array starts, and then an offset for however many elements into the array you're interested in pulling. So what we are told is that the starting address in memory for array A is stored currently in register S3, and that value is 5,000. Take it at its word. They said all the right things. The starting address in memory. Okay, that tells me it's a byte. I don't need to do anything to this. It's already correct. The starting addresses are bytes in RAM. So the starting address in memory is 5,000. Okay, so far so good. And I want the 9th element, so I don't want the 0th or the 1st or 2nd. I want the one that's numbered 8. So how am I going to do that? The way you can do a load word instruction in MIPS assembly language is by using something called an offset, and it's built specifically for arrays. You can give a starting address, and then you can give an offset before it. And that's one of your arguments for a load word. The other argument is the destination, let's say, the place where you want to store that value, and that's the way load word is written. So in this case, my starting address is S3, which is 5,000. I'm okay with that. And the offset that they've typed in here, which you will always see typed in here as a constant, just like this, is an 8. And what that means is 5,000 plus 8. And it can be a negative number as well, 16-bit signed integer, so you can have things that step down from the array. That's handy with stacks, or you can have things that step up into an array. All that stuff's good. But this is incorrect. If you go to that address in RAM, what you will get is the 2nd word, not the 9th one. The first one is bytes 0 through 4. The second one is bytes 5 through 7. That's A0, A1. That's A8. So you'll end up with the last byte, and that's not even an even word boundary. So this is a problem. This is a mistake. I understand why they're teaching us. They're telling us, you tell me which element of the array you want here. Great, got it. But it failed to take into account the word size. It must take into account the word size. So we'll see in a moment the right way to do it. So I'll skip past this a little bit. And let's play along a little bit longer. So let's assume S3 has the value 5,000. And the words addressed 5,000 through 5002 have these three values. What address will be computed by load word into T0, offset of 2 to S3? Well, what is S3? S3 is a base address, and what's its value?
5,000.
Okay, do I go to memory location 5,000 and look up its contents, or is it 5,000? It's just 5,000, exactly. So it's just 5,000. There are addressing modes that'll keep going and going, but we're not there yet. So 5,000 it is. This says add 2 to it. We'll end up with the address 5002, and we're going to load into T0 what is at address 5002, which is 323. So let's see what it's asking. What address will be computed by? So what's the answer? What's the address? 5002 is the address. Winner, winner, chicken dinner. Got it. It's been a while, huh? I have them all. Old ones back to the creation. What value will be put into T0 by load word T00 S3? S3 has 5,000 in it, right? This is 0, add 0 to it. So what's there? 99. So we're saying 99? Anybody going to finish that one, or am I going to have to do it? Bottles of beer on the wall. You guys know that, right? I know that's still used. There's still Boy Scouts out there. It's got to be used. All right, and so forth. And so that's the idea. But because in hardware we actually have this requirement that things be aligned to words, we're really never going to use anything other than, in our case, a multiple of 4. Why 4? 4 bytes in a word, 32 bits needs 4 bytes, all that's correct. Okay, so if you go to memory and you ask for byte 3, this little system that we designed to go and kind of help you get it is not going to know what to do. So what do all of these words have in common? Well, they're all 4 bytes long, and what do these 4 bytes all have in common? They have 32 bits of an address, and you're going to tack on to the end of it a 00, 01, 10, or a 11. In fact, you're going to need all 4 combinations. So if you give me the word address in a register, I'm going to add 2 bits to the end, 00, 01, 10, 11, and that's going to get me all 4 bytes in that word. And it's going to guarantee that it's aligned because this is always a multiple of 4. How do you know this is always a multiple of 4? Well, let's say I gave you the number 5. And I want you to make it a multiple of 4. Okay, we can do that. That's 20. But what's this look like in binary? What's 5 in binary? One, 0, 1. Okay, what's 20 in binary? Okay. What about the number 3? What's 3 in binary? 0, 1, 1. And if I multiply 3 times 4, I get 12, right? Okay, what's 12 in binary? What if I just told you always add 2 zeros? Why does adding 2 zeros work? How do you multiply a binary number by 2? Add a 0. Inside the computer, we just shift it left 1. So if you want to build a circuit to shift something left by 1 bit, would you like to see what that circuit looks like? Here's the container for bit 32, 31, 30, so forth, bit 1, bit 0. To shift it left, you're going to have bit 0, 1, and you're going to have bit 30, 31, and 32 again. And you're going to take a little wire and go like that, and this wire is going to go like that, and this wire is going to go like that. That's how you shift. You just connect wires, but you shift left one. There's no calculation whatsoever to do. I mean, it's literally that stupid. You just run a little wire to the left. The guy on the end walks the plank. He's off the ship now. And what's in the rightmost bit? A 0. If you want to do it twice, you're going to multiply by 2 and then by 2 again, better known as 4. And you'll have 2 zeros. What if you want to multiply by 8? What if we had a 64-bit architecture and your word needed to be converted to a round multiple of 8? Would it be 4? How many bytes are in 64 bits? 8. And how many powers of 2 do you need to get to 8? 2 times 3 times, 3 bits. So if you want to multiply by 8, you shift left 3 bits. It's just that easy. So you're guaranteed, as long as you give me a number and I tack on a 0 at the end of it, it's guaranteed to be a multiple of 4. And then you will also go to RAM while you're at it, and you'll ask for 0, 1, 1, 0, and 1, 1. All right, anybody looked at RAM lately to see, like, physically what it looks like? Let's. And like I said before, I hope it's not the name of a nightclub in Detroit or something, searching for, like, DRAM strip. You know, it's like, I mean, it's happened. I'm like, oh my God, I'm like, I'm gonna lose my job, you know. Stuff like that happens. Let me see if I can find another one. Yeah, well, I've sent out, that one did, yeah, see what I mean? Okay, changed it to Dream Strip, thank you, Google. You know, I do not bear any responsibility for them stealing my acronym. I just don't even want to say, I'll just say this. I'm not even going to say strip. Oh, thank God. Back to Homeland here. Okay, let me see here. All right, we're going to start with this one. So if I go to memory and I want to get something out as fast as possible, I've already established I'm going to get 4 bytes. So let's sort of bury things down. When I ask for the first byte, what am I expecting to get back exactly? What? I have 32 wires. I ask for the first byte. What am I going to get back? How many and what unit do we call it? They're bits. How many? How many bits in a byte? Really? 8, right? 8 bits in a byte? There is a name for 4 bits. Does anybody know what it is? I bet he does. A nibble. Yeah. Old guys rule, okay? Just saying. So, when it was, no insult intended, but we're closer to the same age than the rest of these guys, I think. So, nibble is half a byte. Get it? 2 nibbles make a byte. When we learn about the ARM architecture, you can have the full instruction set for ARM. If you use a reduced version of ARM, it's called thumb. I don't know what happened to hand. Lost along the way, but you have ARM and thumb. That's true. I'm not making this stuff up. So if I want to get a byte out as fast as possible, remember memory is much slower than my CPU, and it's much slower than registers, which are made out of the same thing the CPU is made out of. This is physically separate. You buy it, you plug it into a strip, etc. What would I want to do with those 8 bits if I want to get them out as fast as possible? So let's say this holds 16K worth of memory. How would you organize the bits on this chip? Would you, for example, put, if it's 16, first class, yeah, exactly. Just kidding, can't do that. All right, somebody else with my sense of humor makes me feel at home. Would you put bytes 0 through, I don't know, 2K here, and 2 to 4, and 4 to 6, and just put a couple of thousand bytes on each one of these so you can get 16,000 bytes on this strip? When you go to get a byte, where would you have to go? how many chips would be involved? If you put 2,000 bytes here and 2,000 bytes, oh, I can't believe I did it. You might also like, yeah, I have a feeling I'm not going to like. Okay. 2,000 bytes here, 2,000 bytes here, 2,000 bytes here, and 2,000 bytes here. Your byte is in how many of these chips at a given time? Byte number 638. You know, how many chips would it be stored in? Would it? If you stored bytes per chip and you filled up one chip and then you moved to the next one to start with byte number 2001 and you continued on that way, like you'd fill lakes, you know, when one fills up and the next one starts to fill up, then your byte's going to be in one of those chips at a time. So when you go to get your 8 bits, all 8 bits have to come from the same chip, right? You know, if you're going to evacuate the school, you got 20 buses, and you make everybody line up and you fill the first bus up completely before you start filling up the second bus. And then once that's full, then you start filling up the third bus. Is that the most efficient way to fill the buses? How would you do it? You stripe it, which means what? Well, how would you have answered? How would you fill the buses? He used the right technical term, but tell me how you would fill the buses. How do you do that exactly? At time cycle 1, what would you do? Exactly. At time cycle 1, one kid would get on each bus at the same time. That's one class. The next cycle, the second kid would get on all the buses at once, the second kid from each group. You do it in parallel, right? So if you need to go fast, then this is what you're going to have to do. So how do you suppose we store bytes on these chips? How many chips do you see in this picture on this memory chip? 8. Why do you think it's 8? Coincidence? Why is it 8? 8 bits in a byte. So where do you think my byte is? Byte number 683. Is it on the 6th chip? Use the bus analogy. It's on all of them. The first bit is on the first chip, the second bit's on the second chip, and so forth. So when I tell all of them, give me your 643rd bit, they can all do it at the same time, in parallel, 8 times faster than you do it if they were serial. You would kill for 8 times faster. You are going to be all over that in a heartbeat. So 8 times faster. Now, we said we had a 32-bit architecture, right? So that gets me 1 byte. How many total bytes do I need to get for 32 bits? 4 bytes, right? So what's on the back of this chip? Another 8. How many memory chips do you have to install in your computer at once? 2. You ever wonder why? 2 bytes on each chip, 2 chips, 4 bytes, 32 bits. You get all 32 bits in one cycle, all at the same time. That's why there are all these wires, these little gold-plated things. If you count them, how many do you think there are? 64, at least. So, you know, you're going to have some for the address that goes in, and then some for clusters of 8 bits to come out. There's something different about this one, though. What's different about this one? How many? 9. Why 9? Does this look like the latest and greatest, or does this look older to you? It is older. It's much thicker. You can see that even from the picture. So, you know what parity is? Where you add an extra bit to make sure there wasn't an error introduced? Were the previous 8 bits together, did they make an even number or an odd number? Let's make sure it makes an even number. I'll set the parity bit accordingly. So that's if you have memory and you're worried about errors. We don't usually worry about that anymore. We have other ways and places we'll deal with it. Sometimes you'll find 9 chips for that reason. Right? And people organize these things all different ways. These are all in a line, but there's lots of memory chips that organize things, one vertical, one horizontal, one vertical, one horizontal, and of course I don't see any of them here right now. Okay, a little bit of fun through esoterica with chip design. So I'm going to go to my chip and I'm going to get 4 bytes out at once. And fortunately, I'm going to get them all in one cycle. It's still orders of magnitude slower than the CPU. So I'm doing this because I need every chance I can to catch up. So think about the impact this had. This kept the industry getting 32 bits at once using this double-sided RAM, better known as DRAM, and DDR RAM, etc. That saved us from having to manufacture memory that was 32 times faster. So imagine the cost difference if you had to buy memory that was 32 times faster than this junk. So we keep it as slow as we can, but not too slow, and as fast as we're going to pay for. So this is an engineering solution. There's dollar signs get involved in this. But I can get them all at once. So I'll have a system that'll tell all 32 chips, each one of which has one of my bits at once, the address that I want. And we'll see exactly how we feed it the address in a future chapter. And you'll notice these are multiples of 4. What are these numbers here? They're bytes. 0, 1, 2, 3. And you remember I told you multiply by 4 and you're always going to end up with a 0, 0. If you look at any of these numbers, hide this one, give me a new one here. Okay, why is it not showing me this? I'm screwing something up here. There we go. That's the one that's not hidden. So if I take 0, that's binary 0. 1 is 1. 2 is this. 3 is this. Great. Big news flash, right? What is 4? 4 is 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That'll get me 4, 5, 6, and 7. What about 8? 8 is the same basic idea. We're just going to continue on and add another one. And it'll end in 0, 0, 0, 1, 1, 0, 1, 1. And then we have 12. 12 is 1, 1, and then it has 0, 0, 0, 1, 1, 0, 1, 1. You see they all have the same trailing 4 bits, and all you're really doing is counting word numbers up binary. 0, 1, 2, 3. And so it's very regular. It's very easy to sort of build your system around that architecture. But again, we do this because we want RAM to be cheap, and you want RAM to go in lots of different computers with different architectures. So we don't try to make RAM deal with words. Okay, so let's move down and let's now revisit in the correct way this time the same equation. This time if I want 8, it's correctly represented as 32. That's accurate. So who decided 32? Who wrote that line of code? Did you write that line of code? Who took your A12 equals H plus A8 and turned it into load word with a 32 here, and 12 should be what, 48? And sure enough, here it is right here, 48. Who did that? It's a program you have on your computer. Part of the operating system. It's shipped with the operating system. What do you do with your source code when you're ready for it to run? You compile it. Your compiler does this. This is why you can't take the assembly from one system and port it to another. It depends on the architecture. It has to write code that's specific to your architecture. Maybe the number of registers is different, but it certainly can be the bit architecture is different. All right, makes sense? Okay, S3 has the value 900. What address does this instruction compute? Don't everybody say it at once. What do y'all think? You think that? I heard that from a couple of people. If S3 has 900 and that has 20, that's it. If S3 has 900, T0 has 77, and memory locations, okay, they're going to lose me on this one. So we'll write down memory location 900, 904, thank you, Conrad, for pitching in there. Thank you, Mel, for pitching in, 908. And they have 10, 15, and 20. And we have S3, that's also a memory location, right? It's just a register, it's not in main memory, and it has 900. And T0 has 77. Okay, so far so good. what do these locations have after the following instruction? So we're going to store words. So the first thing is, are we storing T0 into here, or are we storing here into T0? T0 into here, do you all agree? Is that right? Okay, so what's in T0? 77? So 77 is going to go into what? 904, because S3 is 900, and we add 4 to it. So that means 904. So that means this value is going to get replaced with 77. So let's see if we're right. 10, 77, 20. Ta-da! That makes sense? So there's more complicated memory reference models that we can look at later. If you don't have enough registers, sometimes it happens, you spill over into memory. Another good example of a time when you're not going to have enough registers is if you don't know the value, you can't calculate it until runtime. So let's say you have a video game program where you take 10 famous old video games, from Tron to Pac-Man to Space Invaders, and you let somebody pick a number 1 through 10, and that's the program that you'll run. Well, you can't possibly have even one of those programs loaded into registers, let alone all of them. So you're definitely going to be going out to memory and pulling a bunch of stuff in. The compiler can't help you with that. It can't tell you ahead of time, use these registers and do that and have it there for you, because it doesn't know what the user is going to pick. It doesn't know what number they're going to choose. If, on the other hand, you have the user pick A or B, and if they pick A, you're going to run the next instruction. If they pick B, you're going to skip it. That you can have in registers. That's only 2 instructions, 2 lines of code and a branch. So that you can fit if you want. Compiler can help you be prepared for that. So it just depends. Sometimes you don't want to have to go to registers for everything. Sometimes one of the numbers is so small that there's actually room in the instruction. And you guys remember the instructions are 32 bits long. And we have the opcode over here. That's a 6-bit number that tells you, like, add, for example. And then you have a place for 3 registers that are 5 bits apiece. And then there's some other junk over here. And, you know, this is like your target and your source 1 and your source 2. But what if you already know that this value, it's like 8. Can't you let me just put 8 in here? I don't need very many bits for 8. I know you don't have a lot of instructions, but you have enough for that. Why don't you let me use some of your bits? So there's a version of add called add immediate. And in add immediate, you've got your destination, one of your sources, and then you've got 16 bits left over. So this is 6 bits, this is 5 bits, this is 5 bits, that's half. You have the remaining 16. You can put a signed integer in here. Anything from plus 2 to the 15th to minus 2 to the 15th. And that's a pretty decent range. So here's an example of where if you want to add the number 4 to what's in S3, you can just say 4, but make sure you change it to add immediate, because add will think this is a register number, or who knows what. Probably think it's 0 because it needs the first 5 bits, not 16. So let's try a couple here. What are the errors in this exercise? So here's an instruction. Add to T0, SO, and S1. So here's the error. Assume S0 has 5 and S1 has 20. So that should be 5 here, correct? And it should be 20 over here. It'd be a miracle if I don't click by mistake on every single thing I look at here. So the answer should be 25, correct? So is the instruction otherwise okay? I mean, is it a properly formatted instruction? Yep. So I think so, and I think that's the problem. The reason why you may not think so is if you're expecting an immediate in here, and we'll see an example of that. The very next one. If I want to add the contents of SO to the number 44, is this the right instruction to do that? What should this instruction be? Add immediate, right? So since I can't click on this, my only other choice is to click on the offending operand. This should not be part of an add instruction. It should be another register number. What about here? Add SO and 23. And what did SO have? SO had 5. So this was 23 plus 5, and I get 28. So what's wrong with this? This is a constant, not a register number. This has to be add immediate. You can do it, but it's a different instruction. If you make this a constant instead of a register number, you have to tell the computer so it knows how to interpret those bits. You cannot tell by looking at a binary collection of bits what it's supposed to represent. What is this? Is that an integer? If so, is it a signed integer? Is it a floating point number? Is it ASCII characters? Is it an instruction mnemonic? You can't tell. You have to be told. And context tells you everything. So the reason why we have add I is so we know to interpret the third thing as 16 bits and as a constant. All right, what's wrong with this one? 99 plus 5, isn't that 104? So what's wrong with this one? So what's S1? 20. So what should this answer be? 99 plus 20 is 119, isn't it? So this should be 119, not 104. Right, getting the hang of it? Okay, somebody asked, why don't we have sub-I? If you're going to build sub-I on your chip, you're going to be dedicating real estate. Your city is a fixed size. You can only have as many people move into your city as you have houses. And if you only have room for a certain number of houses, then you want to make sure you pick the most important people that'll help you. So if I give you a way of negating any number very easily, I mean, you saw how stupid simple it was to shift left. You just run wires. You can't get any easier than that. And those will run at the speed the electron passes the wires. So if I give you a very easy way to negate a number, such that 6 minus 3, I can show you how to do it as a 6 plus a minus 3, then why do you need subtraction circuitry? Well, you got to decide which one is harder to do. Is it cost you more to have the circuitry that can negate a positive number, or is it more expensive to have circuitry that can calculate subtraction? And it turns out this one is much worse. So we have a very easy way of negating numbers. So if I ask you to write a -3, how do you do it in binary? So I think I heard you say write 3 and put a negative sign bit in front of it. Is that what you said? So let's say it's an 8-bit number, 8-bit architecture. 0, 0, 0, 0, 0, 0, 1, 1. We can all agree that's a positive 3, correct? And the suggestion on the table is that we make it a signed number. That's perfectly legitimate. There's lots of systems that can deal with signed integers. You can feed things. So that means -3, right? Okay, add those together. What should it be? It should be 0. Okay, well, we get a 0 here, and we get a 1 here, and a 1 here. I don't know what to do here. So is that working out so good? So what if I showed you another numbering scheme where you could add, and it would always give you the exactly right result? But this can't be representing -3 anymore. In this system, -3 will be represented by that. So we'll take a look at that in a next coming up lecture. What I want to do at this point is, as I threatened, switch to a different text, because I want us to look a little bit at number theory. And hopefully this isn't something that all of you know. I think I'm pretty safe in saying you certainly understand the concepts, but you won't have heard it expressed this way before. So we're going to switch over to Chapter 9 from the other major textbook used in computer architecture classes, which is by Stallings. And we'll spend a couple of minutes with me trying to figure out how to use PowerPoint and advance to the next slide. Here we go. All right, so what does it mean to be in a decimal system? Well, it means we have 10 fingers and 10 toes, so that's why we chose it. But it means we have 10 different symbols that we use. And we use these. Anybody know where these symbols come from? These specific shapes? Like, does anybody know, I don't know what I did here. I got to the next chapter. Anybody know why this represents 9 and not, that? So let me ask you a different question. What are these numbers called? Yeah, just like that. But what about these? What are these numbers called? Arabic numerals. They're from the Arabs. We use Arabic numerals in most of the world. So, did you know that? So these are the 9 Arab symbols that we use for 0 through 9. If we are writing in a different base, like binary, we only need 2 symbols. Anybody know what an IP address is for your computer? So you can have an IP address that's like 128.249.27.17. What base are these numbers in? Yeah, and so what are the valid ranges of each of these numbers? Anybody happen to know? Helps if you have a little networking. Yep, each of these can be between 0 and 255. So what we call that in math is that's a base 256 numbering system. So what's with the decimal number? Well, in decimal, we were tolerant. We were willing to come up with 10 different symbols. And we went to the Arabs for 0 through 9. And we all know that. It's not too hard to remember. We're successful doing that. But what if we needed to come up with 256 different symbols? Which is what you should do with base 256. You could do 0 through 9, and then the alphabet lowercase, and then the alphabet uppercase, and then you start using like the suits of cards, and then all your little emoticons, and your like graphic symbols, and the Greek alphabet's probably going to make its way in there somewhere, and you're still like 150. You can't do it. No one wants to keep track of 256 different symbols. So we use decimal for that. But the idea behind decimal is you've got these 9 symbols, and their importance in the numbering system depends on their position. 8 does not mean 8 always. 8 can mean 8 or 80 or 800 or 8,000. It depends on the position that it's in. So this number, 4,728, is 4 times 1,000 plus 7 times 100 plus and so forth. So we can build things up by this. A more accurate scientific way that I want to show you is to use the powers of 10. So 83, it would be more accurate to say it's 8 times 10 to the first and 3 times 10 to the 0, because those are the positions that we found those digits. So back to 4728, it's 4 times 10 to the third, something times the second, something to the first, something to 0. And if we follow that scheme, then we can move to any numbering system we want easily. And if we look at a fractional number in decimal, it's the same idea then. The only difference is it's negative exponents now. So as we move further away from the dot, in this case the decimal point, it's going to be something times 10 to the -1, -2, -3, and so forth. So this entire number can be represented by the individual Arabic numeral times 10 to the position to the left or to the right of the decimal point. And you can write a little program to calculate this now. This is something you could add up. You can make it, and how would I do 4 times 10 to the second? Well, if my computer were built in base 10, I would shift it to the left 2. And this would say shift it to the left 1. And this would say don't shift it at all. This would say shift it to the right 1, shift it to the right 2. You remember how easy shifting was, right? You just run wires. So if it's in binary, then I can do that. So think about how to represent a number where all I have to do is take an input digit and shift it to the right spot. It's only ever going to be a 1 or a 0. So that's going to help us do multiplication and division, believe it or not. So here's a table that kind of summarizes what we've done. If I tell you that your number's value is the position digit times its location, then it's basically looks like this. You could make that a summation, just a sum of each of the digits' values times its position. 10 to the whatever it is. If it's to the right, it's going to be negative. If it's to the left of the decimal point, it'll be positive. Okay, consider the number 509. One last thing in here. How many 10s does this number have? Does it have 50 or 0? Well, the way number theory would suggest you approach this, at least for this course, is basically to say you try to hand to the left everything you can. that which won't fit is left over. And that's what you put in your position. So what is in this zero's position is the remainder that exists after handing as many 10s as you could to the left. And what you were left with was 0 because it was an even multiple. It could be 519, which means you handed 50 10s to the left and there was 1 left over that you couldn't hand, so you held on to it yourself. So if you approach a problem this way, every digit can be thought of as nothing more than the leftover from its left. So each digit just has the leftover. If it's 1,000, then write a 1, and there's nothing left over. If it's 1,005, you write a 1, and there's no hundreds left over, there's no 10s left over, but there is 5 1s left over, so it's going to be 1005. So they're getting a little bit more scientific and specific in defining this. How many digits do we need to calculate a number? 99 and 99 are the two largest two-digit decimal numbers you can have. How many spaces do I need to store the result? 2? At least 4. Why 4? Did you guess that because you did the math in your head, or do you see the rule? The answer is 4, and it's not at least 4, it's exactly 4. It's double the size of the numbers you're adding. This assumes they're all the same size. So if you add two 10-digit numbers, you need 20 digits to store the result, sometimes. So in binary, I have two 4-bit numbers. How many bits do you think I need to store the result? 8 is correct. So this is a problem, because if I told you we're in a 32-bit architecture, and all my registers are 32 bits, and this is in a 32-bit number, and this is in a 32-bit register, rather, then I don't have any 64-bit registers. So where am I going to store this result? You're going to have to teach your system how to take two registers next to each other and store the lower significant 32 bits in one and the high 32 bits in the other. And when you print it out for the user, you're going to have to hand it to them that way. So just remember, we need a much bigger space. We need twice the space. And when we look at how to do multiplication, it's going to be like magic, because we'll see where we get those things, where they come from. So this is just to prove to you there really is that many digits. Okay, so these are what are called positional numbering systems. This works in all bases. So in this case, it's base 7. But again, it's number 0 through 6 times their position. 7 to the 4th, 7 to the 3rd, 7 squared, etc. Right, same kind of idea. So let's get to binary. That's why we're all here, right? Only two digits, 1 and 0. And they have the same meaning as they do in decimal. 0 means nothing, 1 means 1. So that's awfully handy. We can still use the same two Arabic numerals again. To represent larger numbers, we just follow the same rule. We take whatever the value is, it's only going to ever be a 0 or a 1, times 2, because that's our base, to the power of whatever the position is. So this means take 1, shift it left by 1, and then take a 0, and don't shift it at all. If I have a number with a fractional part, I'm going to say take a 2, shift it 3 times, or take a 1, shift it 3 times, take a 1, shift it 0 times, take a 1, shift it 1 to the right, take your last one and shift it right 3. I left all the zeros out on this one. I don't like that. The way I would have drawn this example of 1001.101, I would have said 1 times 2 to the 3rd plus 1 times plus 0 times 2 to the squared plus 0 times 2 to the 1st plus 0, 1 again, right? 1 times 2 to the 0 plus 1 times 2 to the minus 1 plus 0 times 2 to the minus 2 plus 1 times 2 to the minus 3. And then I would have shown you this later. But they took all the shortcuts. They left the 1s out because it doesn't change the value of anything to multiply by a 1. And they left the zeros out because those don't add anything to a number ever. So they had 4 1s in here, and they showed you how to kind of get it done. Okay, so let's say we want to convert between binary and decimal. Number conversion between systems is kind of interesting. it's easier to show you the example about what's going on. So the way we're going to do division is by accumulating remainders. Remember a minute ago I said, does 509 have 50 tens or 0 tens? You give everything to the left you can. What's left over is your remainder. That's what you've got in that digit. This is exactly what's going to happen. So I have the number 11 in decimal, and I want to convert it to binary. My base is 2, so I'm going to divide it by 2, because that's my base. So 11 divided by 2 gives me another number in my original base, 5 in decimal, but I have a remainder, and I'm guaranteed the remainder is only ever going to be a 0 or a 1, because I was very careful to divide by my base. If I divide a number by 3, my remainder can be 0, 1, or 2, right? If I divide a number by 5, my remainder can be 0, 1, 2, 3, or 4. But it can't be 6, or 8, or 11, because you would have put more 5s in there. So dividing by the base guarantees that your values are 0 to 1 less than that. So this is what I want to do. I want to collect 1s and 0s only. I'm trying to convert this thing to binary. So 11 divided by 2 is 5, remainder 1. I collect a 1. 5 divided by 2 is a 2 with also a remainder 1. Then 2 divided by 2 is a 1 with remainder 0. And then 1 divided by 2 is 0. 2 goes into 1 0 times with a remainder of 1. So that's my binary number, 1, 0, 1, 1. If I want to do another one, let's take 21. Divided by 2 is 10, remainder 1. Divided by 2 is 5, remainder 0. Remainder 1, 0, 1. That's 21 in binary. This will work great always. Where we get into trouble is with fractions. So if I was sort of shifting things, when I'm dividing by 2, which way am I shifting a number? Shifting to the left adds a 0 to the end of it, right? That makes it a bigger number, doesn't it? So I shift it to the right. So if I have a number like 1001 and the decimal point's here, and I shift it to the right one, I make it a smaller number, right? So this is where I'm accumulating my remainders for multiplication when I'm converting those, and for whole numbers rather. For fractional numbers, I'm going to go the other direction, because with the fractional number, it starts off with everything over to the right of the decimal point, and I'm going to shift it left one at a time. I'm going to turn this into that. So I have to multiply to make that happen, and I'm going to collect these as I go along. So let's see what happens. So here's a number 0.81 in decimal. Anything unusual about 0.81? It's not like Euler's formula or pi or anything weird. It's like a run-of-the-mill, ordinary 81 cents in your pocket. You know, what's the big deal? So let's convert that to binary. 81 times 2 this time. We're going to shed a 1 off the left, and we're going to hold on to it. And we have 62 here. We'll multiply that by 2. We get 1.24, again with the 1. So we'll hold on to it. 0.24 times 2 is 0.48. And that gives us a 0 because that's a 0 to the left. So we take the 48, we move it down to the next line. We do it again. Multiply it by 2. This time we get 0.96 and a 0. And then 0.96 times 2 is 1.92. So we have a 1 here. And then we do it again with 0.92. We get 1.84. We have a 1.84 times 2 is 1.68. Another 1.68 times 2 is 1.34. 1.36. Another one. What's happening? It's never going to finish. So not only do computers guess the next line of code you're going to run, they do a crappy job at math. Does that surprise anybody? Then you think that like computers do math perfectly? I mean, they're like supposed to be the most precise things we've ever invented. They can't even represent 0.81. If you tell it you have 81 cents in your pocket, it can't represent it. It can't do it. So what you hope for is that you have a lot of digits of significance in your numbers, and you string this thing out for 32 bits, 0.8095423, you know, whatever it is, and don't accumulate too much error as you go along. But it doesn't work. You can't calculate it. Sometimes you get lucky. In this case, it's a quarter. So we all know it's 0.01. But let's see, 0.25 times 2 is 0.5. I keep the 0. 0.5 times 2 is a 1.0. I keep the 1 0, I'm done. So that one works. Does that surprise anybody that you can't even calculate like 0.81? So it's not exactly what you might expect. So let's go back over where we were and wrap things up a little bit. The book goes through a little bit of this stuff, but I kind of wanted everybody to be on the same page with what this looks like. So here's the positioning thing we were talking about, the value 1 or 0 times its position, and you get your result out of that. Here's a binary number tool that'll let you put in 1s or 0s wherever you want. One other thing that's kind of interesting to know that I'll point out here is you'll notice that if I have a string of 1s together in a number, I can represent it. And in this case, I have a big string of 1s. I have 7 of them together, right? And I could calculate it this way, or there's another way to do it. I could calculate it as the first 0 off the left-hand side, which is, in this case is 128, minus the last one on the right-hand side before I got to more zeros again. And that would be 128 minus, the last one was here, minus 1, which would give you the same number, 127. So there's a formula that we're not probably going to take a look at, but I'll tease you in case you want to go look. You can represent all binary numbers as some collection of bits. Here's a string of 1s, here's a string of 1s, here's a string, here's a string. Every one of these can be calculated in binary by saying, replace this, let's do this one, replace this with as if this were 1 minus this one, and ignore the other ones in the middle. For this one, treat this number as if this had been a 1 minus the last one, and ignore these in the middle. So let's see if that's right. This is 0, 2, 4, 8, 16, and 32. So this was 30. This is binary 30. Do you guys agree that 16 plus 8 plus 4 plus 2 is 30? Okay, so I could calculate it this way by taking 1 times 2 to the 4th plus 1 times 2 to the 3rd plus 1 times blah, 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 blah. Or I could just say 1 times 2 to the 5th, which is 32, minus what was my least significant one? 1 times 2 to the 1 minus 2 gives me the same thing. So there is a way to build a combinational circuit in circuitry that does things this way, and it's faster. It's maybe 25% faster, and you better believe we'll jump on it all day long. It's called Booth's formula, and it's not in our textbook, but it's kind of a cool program to write. You basically, the zeros don't matter. We just saw that a minute ago. Remember at the bottom of the slide, the guy just threw all the 0 ones out and just left the 1s? Those are the only ones that change your number. So it's there's kind of some interesting theory. People have gotten a lot of interesting stuff done with this. The very last, yes, B-O-O-T-H. You'll see it probably called Booth's algorithm. And it's in the Stallings book, for example. The very last thing we'll talk about in this section is back to the Excel example again. If you hand me your 32 bits, these are your 4 bytes, and bit 0 is always going to be on the right, bit 7 is always going to be on the left for each of these. That's kind of universal. And you want to store them in RAM, and here's your 4 bytes in RAM. Which one do you put here? Do you put this guy here, or do you put this guy here? Believe it or not, systems do this different ways. In fact, with ARM, you can pick which one it does. One of these is called, are you ready? Big Indian and Little Indian. Yeah, if we did this today, pretty soon we're going to be calling this Big Texans and Little Texans, or Big Pandas or Little Pandas, or something that's not in the least bit offensive to anyone. We would probably not call it this way these days, but at least it's not spelled the same. But this is called Indianness. What Indianness is your system? Do you use Big Indian or Little Indian? And this textbook does talk about it. But this has to do with which sequence you put these things in. And different computers do it for good reasons, different ways. And like I said, ARM, you can pick. When you're going to deploy it in your phone or something, you can set a bit that tells ARM store all of your words in little or big Endian format. So back to Excel. If I hand you my Excel file, how are you going to know which order to pull the bytes out? I mean, maybe we agree we both have 32-bit architectures, and you're like, oh, yes, I don't have to worry about it. Really? Want to bet? So one of us is big Endian, the other is little Endian. Both systems exist. So that's another thing that we have to be careful of when we design some sort of intermediate file format. And just to kind of cut to the chase, because the book doesn't, this textbook and this course don't talk about it, you have an intermediate file format that you store everything, and you indicate the format that you've got. So if you look at the bits in an Excel file, they're going to be the same for every system, because everybody writes to an intermediate agreed upon file format so that you could move that file and open it on any other system and it'll know what to do. This is a huge issue with floating point numbers when you're sharing scientific data with other people. You pull a little card off a Raspberry Pi where you've been collecting vibration data and you stick it into your laptop, boy, you better be knowing exactly what's going on, because you cannot make any assumptions about the bit size and the order and the sequence and how floating points are stored. Are they signed? Are they unsigned? Is it 2's complement or 1's complement, or you don't get any complements at all? Or, you know, it's like the Rodney Dangerfield joke. And the 2's complement's the number system we'll use, but, you know, he goes to the doctor and the doctor says, you know, you need to lose some weight. And he goes, well, I want a second opinion. He goes, okay, you're ugly too. Okay? So 2's complement would be nice haircut and I like your shirt. Right? So we'll learn about that numbering system next time. You have homework, right? Everybody know? Okay, if you're not getting emails, we found a student who, it happens every semester. I have no idea how it happens, but they had their address in with the registrar and they're not getting any emails from the class. So like they missed one of the homework due dates, and so that's kind of the worst case scenario. But what I said was no email, no homework. They are going to get a break. And that's why Homework Solution 1's not quite out yet, is because we're trying to make sure we have all the beginning of semester things ironed out. You will see that out. When it's out, it'll be on the Google Drive. So tackle the homework and make sure you're reading Chapter 2. I think last time I gave a deadline for the chapter exercises, and after that date, Zybooks just stopped giving anybody credit for anything. If that is in fact what happened, everyone will get credit for all of Chapter 1. And I just won't put any due dates on except like the end of the semester. But I will tell you when I'm going to pull the grades for that chapter. So we'll just talk about it. Okay? All right, guys. Have a great couple of days. Yeah, well, forget that. That's not going to happen. You're going to get 100. So.
Has homework 1 been graded?
It has by some TAs.
Okay, so I shouldn't be freaking out yet, because
there was an error in the solution. So if you see that it's graded wrong against the solution, it's because I changed the solution after they graded it.
Okay, I actually...
Little switcheroo.
I haven't gotten my grade
But if it
yet.
doesn't add up to 30 points, it's not going to change your grade 1 point. So accumulate some of those.
I just wanted to tell you that I'm a douchebag. I did mine in LaTeX, and I want to know if that's okay.
Yeah, I don't care. They'd love it.
Okay, good.
It'll probably make your grade go up. When I went to Rice, the Mac had just been invented in 1983, and I bought one and did all of my homework assignments in Write, which was the name of their word processing program, and it was the first one other than LaTeX. It had all that. Yeah. And my girlfriend and I, we turned in the same homework, and I always got a higher score, and it completely made her mad. And I'm like, you know, appearance is important. What can I say?
Whenever I had to show your work, right, and what I would do is I type it in LaTeX and then copy like a PNG of like a screenshot and paste it in Word. And after like 20 minutes of that, I was like, fuck this. So I just wrote the whole thing.
You know how to use the
text.
equation tool in Word?
I actually don't even have Windows on my machine, so I was trying to do it in what
Google. So there's
LibreOffice is what I was using.
Yeah, so there's also Google Docs has some good equation stuff too.
But I mean, you can't get the quality formatting like this, right?
Well, I can't. You can, but I don't.